Hello, fellow scholars. Today we are going to do some talking about sets, whole numbers, number theory, numerations, and computations. And this is all going to be a form of mathematical communication. What we're first going to talk about is sets. You may be thinking, what is a set? Well, a set is a collection of objects. And this is a way that mathematicians communicate with one another and, scientists and people of the nature. So sets make it possible to organize and classify and describe the elements or the members of a set. And trying to get that off there. These sets are represented by Venn diagrams. And we start out with a rectangle that contains the universe, and the universe is going to be all the elements or members allowed into consideration for the sets. And then we're going to arrange each set by each circle, and sometimes they overlap. Now, our universe is going to contain A, B, C, D, E, F, G, and H. And within the universe, the set A is going to contain B, C, D, G, and H. B will contain D, F, and H. C will contain D, G, and H. So our first goal is to figure out unions and intersections of different sets. What I mean by this is a union, these are going to be represented by caps. This is what this symbol is called, a cap. A union basically just means both sets combining. We're going to combine the sets. And then an intersection is what is in both sets. We're going to use this like an and. It's going to be in this set and this set. And we may even talk about things like a complementary of a set and things. We'll get to that in a moment. First, let's try to figure out what is B, and we're going to say union C. We're going to open a bracket, and we're going to see where B and C, what union is B and C? Well, first, let's go ahead and fill out our Venn diagram. That's going to help us out a lot. So we're going to go look through here and see what do these sets have in common? Which elements are they in common? So we can look at B and see that it's only in set A. So we're just going to write a letter B. And then we can do the same thing for C. And then we're going to get to the letter D, and we realize that D is contained in all three sets. So let's go ahead and write it where all three circles overlap. And then we're going to look at letter G. We can see that that is in set A and set C. So we're going to go ahead and write where those two circles overlap. And then again with the letter H, we can see that H is also in all three sets. So we're going to go ahead and fill it in right here. And then the letter F is in set B, and then we are left with the letters A and E, just hanging out in the universe. Okay, so now looking at our Venn diagram, we can see that whenever we union B and C, we're just going to say that these are the elements D, F, G, and H. Okay, and now we're going to see where the sets A and B intersect. A intersect B. So let's check out the elements that are in both A and B. Well, when we look at our Venn diagram, we see that the only two elements that these sets share are going to be the letters D and H. Okay, let's try to see where B intersects C. Okay, it also looks like these share D and H elements. Okay, let's try the union of sets A and C. So we can basically just copy through here. We see that B, C, D, G, and H union the sets A and C. Now we're going to talk about a complementary set. This is going to be all the elements that are not in the set A, that are in our universe. So whenever we look around at our set A, this circle here, we see the only elements that are not there are the elements A and E. So now let's see where A intersects C. We can see that they both share the elements D, H, and G. And now we're going to use the associative property to bring a union between B and the intersection of C. And we're just going to distribute A. We're going to bring together all the elements in B to right here to this. So we already have D and H. Let's go ahead and write those because they don't need to be in any particular order. As long as they're in the set brackets, we know that they belong together. And we're just going to go ahead and add all the other elements that are in A. And then we have G. All right. And that is going to basically teach us how to break down a Venn diagram and check out how sets really work. So let's try to apply this, what we've learned, to another style of chart and sets. These sets are going to contain shape and color elements. So let's use this key, and we're going to let these letters represent these items. Let's try to figure out where large intersect hexagonal. So this is basically means that this is all shapes that are large hexagons, because we want the shapes that are large and hexagonal. Now, let's try to see what this is going to be, the union of shapes that are circles or hexagons. So this is going to bring them together. We're going to see circles or hexagons. And now we're going to look at the things that are not triangles and red. And finally, we are going to look at the circles that are small and red. Wow, sets are pretty cool. Okay, so thinking about sets and numbers and number systems and things that we can communicate with numbers, we think about, when we think about place values and all these things, we think in a decimal system. We think in the base 10 system, most likely because we have 10 fingers. When I say base 10 system, let's think about a number like this. How would you read this number? We would probably look at it, if we put our commas here, we would call it 1,725,684, right? Well, these place values here have a name. This is our ones position. This is our tens position, hundreds. Then it moves to thousands, 10,000s, 100,000s, and finally 1 million or millions. Now, what I did here was raise each position to the next power of 10. Like this would be 10 to the 0. And then here we would have 10 to the 1, 10 to the 2, 10 to the 3rd, 10 to the 4th, 10 to the 5th, and 10 to the 6th. We see that we have 6 place values. And whenever you multiply 10 times 10 times 10 times 10 times 6 times, you get 1 million. So this is going to be our base 10. And we know this number system, but this hasn't always been around. Societies like Egypt and Egyptians used a system of hieroglyphs for their numbers. And so we can take a look at their charts and all the imagery that they used, and we can try to break down what this number might be. So what we would do, we would first take these symbols because they're all alike, and usually whenever people group symbols together, it's meant to be counted as one number. So we're going to add 10,000 times 3. Then we're going to add that to, we have 10 times 5. Then we're going to add that to 4 times 1. And this is going to be, 30,000 plus 50 plus 4. So this number is going to be written like this. See, that's something we can recognize, although it is pretty cool looking in the Egyptian times. So now let's look at another system that we may be more familiar with. This is going to be our Roman numerals. And we've probably seen these on, clocks or the sides of buildings, or maybe somebody's tattoo they may have. And the difference is, instead of using a base 10 like us or the Egyptians did, they don't even use a base system. They use more of a pattern, and it's going to be like times 5 times 2 times 5 times 2 times 5 times 2 and so on. But these are the most common elements that they use in these numerals. And so we're going to try to use these to solve this chart. Remember how earlier I was saying that they group together, it's usually representing one number. Well, the difference in Roman numerals is this represents 1,000. But this number, see how they're different? It's separated. This is going to be a subtraction. We're going to use addition and subtraction in Roman numerals. So we're going to take 100 away from 1,000 because it's before. And we're going to say that this is 900 because it's going to be 100 lower than 1,000. And then this next group is going to be 30 because 3 times 10. And then we're going to have a 5 and 2 1s. Or if you become more familiar with Roman numerals, this number here represents 7. But we can get there by adding it all together. So let's say 7. So this number is actually going to be 1,937. Let's go back a little further in time. And we're going to look at the Babylonian system. This is a very simple system, and it's just 1s and 10s. Pretty simple enough. So we're going to say 10, 20, 30, 40, 1. 41 is this number. Now we're going to go to a little bit more complex of a number system, and then we're going to look at the Mayans number system. This is one of their 2 number systems. They actually had a much more complex system that they used for calculating very large numbers, astronomical numbers even. They made several calendars, but first we're going to break down this. And you can see that the Mayans use a base 20. So how we were talking about the base 10 and all those systems earlier, we're going to say 20 to the 0 power, 20 to the first power, 20 to the second power, 20 to the third power, because we see we have 4 places here. So whenever we write this out, what we're going to have to do is we're going to have to take this number here that we see at the top. This number is going to be 5. And we're going to multiply that by 7,200, because that would be 20 to the third power. And then this next number here, we're going to say 6. And this is going to be 6 times 360, and then we're going to 3 times 20, and we're going to add together 17 times 1. So let's go ahead and do 17 and 60. We could do some calculations over here or use a calculator. Let's see. This is going to be 2,160. And then we're going to multiply 72,000 times 5. And it's going to give us 36,000. So now we're just going to go back and we're going to add all these numbers together. Let me hold my screen so it doesn't keep moving. 36,000 plus 2,160 plus 60 plus 17. And now, whenever we add this, since we use a base 10, we're going to use what we call carry, or it's actually just an exchange. We're going to exchange one value for another. So this is going to be 13, but we're going to carry our 10, our 1, to the next place value. This information is going to come in handy in a moment, I promise. And then we're going to add these together. So this system of symbols is actually representing the number 38,237. They may be on to something there with using symbols instead of writing all that out. Okay, so you notice how we wrote all this out. We had to calculate all these things. There's an easier system of figuring out numbers, or an easier way to do multiplication, So we can chart out all these numbers and carry and this and that, or we can use the lattice system. And this is just basically going to be, we're going to make sure we have 2 digits at each box for each digit. So we have 2 boxes on top and 2 boxes down the side, which is going to give us 4 boxes. And then we're going to divide each box into 2. We're going to keep our places. We're going to work left, right, and down. So what we're going to do is we're going to take these 2 first factors, 2 and 3, and we're going to multiply them together, and we're going to record it here. This is going to, since we're using the base 10, we have no 10s, and we have 6 1s. We can keep working down the lattice. We're going to say this 2 times 2 is 4. And then we're going to say 8 times 3 is 24. And 8 times 2 is 16. Now this is going to be the fun part. We're going to take these diagonals here, and we're just going to add diagonally. So we're going to start in this lower corner, and we're going to just bring this 6 down because there's nothing to add it to. And we're going to say 4 plus 1 is 5, plus 4 is 9, and then 2 plus 6 and plus 0 is 8. So our total for 28 times 32 is going to be 896. Seems simple enough. Let's try it on, let's add some more digits. Just try it out. Okay, we're going to multiply, 3-digit numbers. So let's go ahead and say 273, same principle, 628. Let's go ahead and start with the number 3 and work down. So 3 times 6 is 18. 3 times 2 is 6. 3 times 8 is 24. 7 times 6 is 42. 7 times 2 is 14. 7 times 8 is 56. 2 times 6 is 12. We have 4 and 16. Okay, here we go. This is where it's going to get a little bit more interesting because we've got a lot more diagonals to add here. We're going to bring down our 4, and now we have 6 plus 2 is 8, plus 6 is going to be 14. So what we're going to do is we're going to bring this 4 down, but we're going to carry our 1 here. So 1 plus 8 is 9, plus 4 is 13, plus 5 is 18, plus 6 is 24. Doesn't feel right, but I bet it is. So we're going to bring our 4 here, and we're going to bring this 2 over here. And then we're going to add diagonally still. We're going to say 5, 6, 7, and 11. We're going to bring this here. 5, 6, 7, and we're going to say 1. So now this is going to be our total here. So our answer is actually going to be these numbers here. We can put a comma right here. So 1,700 or 171,000, I'm sorry, 444. Okay, that one confused me just a little bit. So let's go ahead and try another 3-digit just to practice some more to see if we really are getting it before we move on to something a little more complex. Practice is always good. So we're going to say 4 and 5, 4 and 9, 6 and 5, 6 and 9, 6 and 3, 9 and 5, 9 and 9, and 9 and 3. So again, let's go ahead and draw our separations here, that way we don't lose track of which numbers we're adding together. And drop our 2. We're going to say 15, carrier 1, 8, 9, 16, carrier 1, 8, 9, 10, 11. Oh, we got to carry this 1 too. So 9, plus 8, 17. And this number here, our answer is going to be 571,652. And I bet if we were to put that in a calculator or do it the long way we've learned, that we would come with the same answer. Now let's try adding another digit into the mix. We're going to use a different kind of chart. We're going to write it here. And we can really add as many numbers as we need to, just as long as we make sure to keep it correct. Because if we added a 0 in there, that would change our number. They don't have to balance. They just have to match the amount of digits that we're starting out with, because this would completely change our total if we added a 0 at the bottom or somewhere else. We don't want to mess our numbers up. 5 times 4 and 5 times 3. 27, we have 8, 16, and 12. Again, we're just going to drop this here. Drop this and carry our 1, 5, 6, 13. Carry our 1, 3, 9, 11, 13. Carry another 1 here. This is 10, 13, 15, 20. Drop our 0. We have 12 and 1. So now this number is going to be 1,203,336. Now that's all good. So we know we can use this lattice to help us do math or multiplication. But there's another way too. We can estimate. Estimation is a good tool to learn. Oops, I have zoomed in. Okay, here we go. Now, what we're going to do is we're going to take our leftmost number and we're going to round it. Now, if it's 5 or higher, we round up. And if it's 4 or lower, we're going to round down. So, to estimate this problem, we're just going to say we could lower it up to 900, or we can lower it to 880. Usually, people like to use even whole numbers. So let's just go ahead and try it 2 different ways. We're going to estimate it with 900 plus 500 divided by 100. And that would give us, what, 14? I did too many zeros. Whoops. All over 100, which is going to be about 14. Or we could say 880 plus 470 over 130. And that would give us or you know what, I would actually round it to 135 just because I see that this is an even number here. And we'd be able, to give us about 10. That would be a better estimation. Personally, I would try to get it as close to a whole number. That would even up to make it mentally easier. Now, we can actually directly calculate the exact amount that it would be. So let's go ahead and say 883 plus 465. We're going to say, remember to carry our 10 here. So 1348, all divided by 134. So we can see that we have, this is all going to cancel out, and we're going to end up with 1 with a remainder of 8 over 134, or this would be a decimal somewhere along the lines of, so this actually would come out to be 10.059 or something of the likes if we were to actually use a calculator. I was just trying to mentally do that multiplication, and I probably should not. I need to pull out a calculator. So let's go ahead and try another one. We're going to do some more estimation. This is kind of cool. So we can say 5 times 250 plus 525 over, let's just say about 40. Okay, I'm going to pull up a calculator really quick. Maybe I have. Okay, here we go. Let's just do 5 times 250 plus 525 divided by 40. And that's going to give us about 44.375. Now, let's go ahead and calculate it exactly to see what we would get. Okay, we're going to say 5 times 254, and that's going to be 1270, and then we're going to add 523, and then we're going to divide all that by 42, and that's actually going to exactly equal 42.69. So if you look at it, estimating is actually a pretty good way roundabout. You would rather overestimate slightly so you can have little to work with than sell yourself short and not have enough. But really, we like to get pretty close to the answer we're looking for. And 44.375 is pretty close to 42.69. So I'd be happy with that. Let's go ahead and try another one. This one is going to be a little trickier just because we already have a couple whole numbers to work with. So one thing we could do would be to just say 600 plus 400 divided by 300. And that's going to give us, 1,000 over 300. So that's going to give us about 3.3 repeating. Okay. Oh, I just realized that is a multiplication symbol and not, in fact, an addition sign. So we could either use our lattice method that we learned a second ago, and we could, we're going to completely delete that. We could use our lattice method, or you just, if you already broke out a calculator, just go ahead and do that. 266,600 is going to be the total of this top. And then we're just going to, if we were, oh, wait a second, we're estimating on this side. I'm so sorry, I've lost track. Here we go. Let's just say 600 times 400 is going to be about 240. 1,000. And then we're going to just divide that by 300. So let's cancel out these zeros. And then we left ourselves with 2. And it's going to be about 800. So let's just say our estimate is about 800. I'm so sorry for all that confusion. Now let's go ahead and total it up exactly. We already know that this is going to be 266,600. And we're going to divide that by 293. So let's go ahead and use our calculator. And it's actually going to equal exactly 909.9. Or if you wanted to use 3 decimals, it would be 8.898. All right. So earlier we were talking about bases. And we decided that we are familiar with the base 10. So we need to learn about some other bases. So we're very familiar with the base 10. We talked about that. So another base that's pretty popular in mathematics would be the base 5. And I personally think they like to use this because it's a lot easier to count on one hand than it is to count on two. And so when we're thinking about base 5, we are going to be thinking in exponents of powers of 5. And I lost my little stylus. Here we go. Okay, so this is going to be our 5 to the 0 power, 5 to the 1, to the 2, 5 to the 3, 5 to the 4. And this is going to represent 1. This is 5. And then we have 25. 1, 25. Is it 6? Yeah, 625. Okay. And so, and another base that is used would be the base 6, which is basically the same principle, except for now we are using powers of 6. I've lost, here we go, from current. Here we go. Okay. Base 6 is basically the same concept. It's just 6 to the 0, 6 to the 1, to the 2, 6 to the 3, to the 4, 6 to the 5. So this is going to be our 1, 6, 36, 216, 1,296, and our 7,776. We can see why we like base 10 better. But then let's go ahead and try to figure out this problem here. Let's just write it 4, 3, 2, and we're going to do a tiny little 5 because we're a sub. It's a sub. And then we're going to add together 1, 3, 3 base 5. And now, see, we can't use the number 5, so we're going to have to carry or exchange it. So this 2 plus 3 is actually going to roll over into, we have 1, 5. So we have 3 plus 1. Well, that's going to give us 7. So we're going to exchange. We're going to write a 2 here, and we're going to exchange that 1, 5. And then again, we can't write a 5, so we have 6. We're going to have to carry that 5 here, and we're going to put, so we're going to sub 5 that. So our total for 432 base 5 plus 133 base 5 is going to be 1,020 base 5. And now we're going to, this is how we would write that number. We're going to look at a base 6 problem. So whenever we're adding together base 6 plus 73 base 6, now we have to remember we can only go to 5. We're on 0, 1, 2, 3, 4, 5, and then it rolls over at 6. So we're going to take 8 plus 3, and this is going to be 11. So we have one group of 6 that we can exchange, and we have a 5 left over. So let's take 1 plus 2 plus 7 is going to be 10. Again, we only have one group of 6 we can exchange. We have a 4 left over. And then 6 plus 1 is 7. That's going to give us 1. And then we have an extra 6 here. So this number is going to be in our base 6. Oops. Base 6. If you write them too big, it starts to look like a different number. So I got to be careful with that. We all should. Okay. Now that we know this, let's do some subtraction. And you might be thinking, okay, this is going to be a lot more difficult because how do I borrow from what I don't have? And honestly, whenever you're talking about it, it's kind of hard. So whenever you're thinking of subtraction in base 5, it's easier to use a chart. And you're going to use what's called a chip chart. And you're going to write out the groups that you have. So we're going to do our place values. Remember, this is our 25s, this is our 5s, and this is our 1s. So we know that we have 4 1s, we have 1 5, and we have 4 25s. So whenever we're taking away, we can't take away 3 from 4. So let's go ahead, and that leaves us with 1. But you can't take away 4 from 1. So what we're going to do is we're going to take one of these 25s, and we're actually going to convert it because there are 5 5s in 25. Now, that gives us 6 5s. So what we're going to do is we can take away 4 from 6. So that's going to leave us with 2 5s. And now we have 3 25s. So whenever you're subtracting, you have to think about things slightly different than we would in a base 10. Let's try another one. Let's still use our chart, and let's go ahead and do some more subtraction. So we've got 503 base 5 minus 24 base 5. And again, we've got 5 25s, we've got 0 5s, and we have 3 1s. So we can't take 4 away from 3 1s. We don't have any 5s to borrow. So we're going to have to take away from our 25s first. So let's go ahead and take away this 5, and it's going to give us 25. It's going to give us 5 5s. And now we can borrow one of these 5s, and it's going to give us 5 1s. We can definitely take away 4 from this. So we're going to take away 4. That's going to leave us with 4 1s. Now we have 4 5s, and we have 4 25s. Okay, that was pretty fun. So I think we learned a lot about number systems and all the different types of computation. So maybe the next time when we're thinking about numbers and how symbols can communicate and all these different things, maybe we can think about things a little more mathematically.